All right.
Okay, well, so we'll push on to the next presentation. So Sash is, I'd say, focus heavily on experiments. I probably should distinguish between physical and numerical. It'd be fair to say the numerical experiments.
Yeah.
All right, I'm trying to cover myself here.
No, that sounds good.
So in that case, I'll go ahead and let Sash take over.
Thank you. Thank you also, guys, for inviting. This has been definitely a fantastic workshop so far. So I just wanted to say a couple of things. When I was giving my talk in the last workshop, I gave kind of a research talk, and it seemed like it was a sort of the theme there was a little bit more tutorial oriented. So I'm going to show some generic results from microstructural modeling, and then I'll show some research results too. So a lot of the work that I'm going to show here, well, several funders, collaborators, and former students, current postdoc, lots of people. So I'm going to talk about roughly 3 sections. First, I'll talk about the basic formulation of microgeodynamic models. These are the models that I use to quantify microstructure, and especially Yasuko has set up the background for my talk quite nicely, actually. I'll discuss a little bit about the solution methods, and then we'll look into 3 different types of applications, because it seems like since I started this whole business in 2008, there has been some quite interesting and almost unexpected developments where I wasn't quite sure that these applications will come out of these type of models. So I'll show using some seismic inversion, some forward modeling, and also 2-phase flow modeling. So the idea here is to copy what a wise person said yesterday. We start from the frog's eye view, and then probably move on to a bird's eye view. Okay. So there's another little icon I need to explain. So as I said, that I kind of want to keep like a tutorial, so there will be some general stuff that I'll talk about. But there will be times when I'll do some shameless propaganda of my research, and those slides will be typically marked by this little icon. Okay, plenty of humor. So I cut down a lot of slides that I had here that defined contiguity. I think after this morning I don't need to really go into great details about what contiguity is, but I'll just bring up really quickly a couple of things. So first of all, the way I like to think of this, it's the fractional area of grain-grain contact in a partially molten aggregate. And one way to define contiguity mathematically, oh, by the way, my contiguity is Uli's wetness, so my contiguity is 1 minus this psi is 1 minus Uli's psi, so they are going to look opposite, okay? So one way to define this contiguity in a two-dimensional model, and you could do sort of the same thing for a 3-dimensional model, but you define this function called the contact function x, and then this function takes the value of x equal to 1 at the grain-grain contacts and 0 at the grain melt contacts. So, and I think when Dave Berkovici gave his talk in the first session, he gave a very, very nice description of where that function comes from. I'm not going to get into that. What I do want to show here is this little bit here. These 2 ends, these are unit normals on the grain boundary, and this is an outer product, okay? So what that means is you actually do have a tensorial quantity. Now, the issue that we will look at is, under certain conditions, this could be an isotropic tensor, and you could just use the trace of the contiguity to define what's going on. But especially when we get deformation, this tensor starts to become anisotropic, and that has quite a lot of implications. And I'll just show one implication for the lithosphere-asthenosphere boundary. Okay, so we'll just keep that in mind, and let's move on. So So just a little bit of a history. There has been, in kind of my way of thinking, I would say that the classes of models of microstructure probably would be, I'll put them in two different categories in the classic work. So the first one I'll call geometric. And von Bargen and Waff, we talked about that paper quite a bit today. There's also Randall German, who did a lot of work on liquid phase sintering. Ray had a classic paper in 1976 on the microstructure of multiphase material. So most of these literature would do something where you would, your geometry would result from some sort of minimization of surface tension. And the really strong advantage of this group of models, as we have seen already with von Bargen and Waff, you can get very nice values of contiguity out of these. Okay, these models work perfectly if you are working without any deformation, because of the fact that these models are primarily geometric and don't take into account deformation and stresses. They don't really work when you have deformation. Now it turns out that there has been quite a lot of work, especially in the 1990s. If you look into the Journal of Fluid Mechanics, there's just many paper, but my favorite ones are Quicken and Hopper, some by Kwon and Messing. So these people were trying to look into some fluid mechanics based dynamic model of microstructure. And for these models, the driving force really was to understand, when you're sintering powders, how the area of the contact, as they call it the neck, how that area of the neck grows. The idea being, if you have a wider neck, in other words, if you have a higher contiguity, you'll have a stronger material. I'm going to show in a second a couple pictures from these models. Basically, the problem with these models is, the advantage of these models, they can, because they are fully, they solve the mass and momentum conservation equations, so you can take into account for deformation. But things like dihedral angle or contiguity are not very easy to get out of these models. And so what my group has been doing to kind of get the best of both worlds, we decided to try a different approach, and we go in a multi-particle way. So instead of using a single grain, or a single domain, which was done in dynamic models, we solved these equations for multiple domains, and I'll show these in a little bit. And then we apply boundary conditions across, which also allows us, because we have multiple grains, it gives us the advantage that we could do these geometric properties, while we can also take into account the dynamic models. Okay. So just an example of the paper by German and von Bargen and Waff. These are geometric models, and so these are a couple of dynamic models that were done in the early 90s. So this is by Hopper. He had quite a few papers actually, which was about the coalescence of cylinders, and you can see that as the time passes, this sort of pinch out area becomes straight, and that was all that they were going for. So here is our approach on how we handle these equations. So first of all, this is a very schematic diagram. We take a partially molten rock as something that behaves in a very similar to a suspension. We can control the density of the particles, and then we can go into we can vary the melt fractions. But let's just for a second, let's consider we have a suspension of a number of particles. We'll designate each of these particles or grains as K. The fluid itself is another phase. So if you have n particles, we have a total of n plus 1 domains. Within each of these domains, we solve for conservation of mass, conservation of momentum. So T is the stress with the pressure included. You have a no-slip boundary condition. And very importantly, we have this stress jump condition here. Okay, so it's worth spending a couple of minutes looking into this equation. So the quantity on the left, it's the difference in normal traction across the grain boundary. Okay. Now, actually, I should take that back. It's not normal traction. It's traction across the grain boundary. So this is a vector boundary condition, and it has two components. it also turns out that the first component on the right-hand side is directed solely along the normal, and the second component on the right-hand side is purely tangential. Okay? So if we were to take the normal component of this boundary condition, then what we would get is basically the very classic nice equation we have for a soap bubble where delta P is equal to twice gamma over R, which is called the Laplace equation. So we call this the Laplace term. The second term here is called the Marangoni term. I have a delightful slide about that coming up. But basically, the Marangoni equation arises from the fact that you might actually have variation in the properties of surface tension along the surface of a grain. So Uli showed us these beautiful images where it was pretty obvious that in the grains you do have various surface tension. So I'm kind of showing an image here. This is just sort of giving you an idea. If we had a grain, in this specific case is an isotropic grain, you have a different surface tension at the grain-grain contact, different surface tension at the grain-melt contact, and this Marangoni term here captures that variation along the surface. Okay, so the Marangoni effect. Carlos Marangoni did his PhD, I think, in the late 1890s on these things. These are called Marangoni tears. We'll probably test them out at the wine reception. But basically, what happens when you take your glass of wine and give it a little swirl, alcohol starts to evaporate, okay? And the evaporation has a characteristic wavelength of the wine. And as a result, the spacing between the strands is covered by, because you're evaporating alcohol, you're changing the surface tension along the boundary. And hence, it's called the Marangoni effect, and that's a Marangoni convection. So we see that basically same term appear in our grain boundary processes where you have a variation in surface tension at the grain-grain contact versus grain-melt contact. Okay. So those were the governing equations. So just keep them in mind. We are solving for these partial differential equations with the coupled boundary conditions. And how do we go about solving them? So there are a couple different ways we have gone about it. The quick and dirty, easy way is to do something called semi-analytical method. My student Jesse Weimert did his master's project on doing these things. Basically what we do, I'll show the solutions a little bit, but basically we do a spectral model, essentially. So we take the linear limit of our governing equations, and then on that linear limit, we use spherical harmonics transition. So it's very, very easy to calculate, very quick to calculate. We could vary the melt fraction quite a bit. We cannot go to very low melt fractions here. So that was the sort of drawback for these models, but again, they're very easy. The other process is solving these equations numerically, and I chose boundary elements method for the numerical technique of choice. There are other ways you could do this, but boundary elements method gives us a lot of advantages. The big advantage of boundary elements method is when you're solving for different types of particles, you could actually take the PDEs, partial differential equations, and change them into integral equations along the boundary. By doing so, you're reducing the dimension of the problem by 1. So when you're solving a problem in 2D, all you are doing is a line integral. So that makes it a little bit easier to solve. The difficulty along with the boundary elements method is you run into things like singular integrals, and really massively one big problem is when you discretize the equations, you end up with a very dense matrix. So when you're solving the system of linear algebraic equations, it's really hard to get to very large number of grains. So I'm going to come to that in a little bit. The other advantage of using the boundary elements method is also because we want to study the deformation of the grains. The shape of the grain is one of the variables in the equations that I had shown before. So we actually know the position of each grain at each time, so we can do quite a lot of stuff with that.
Why is there a plug in the corner?
So this is my research. So hence a shameless plug of my own work. So some text.
Honest approach, right? Yeah.
Well, I mean, if I were giving a research talk, I wouldn't do that. So, I mean, some of us probably know about these books, but these are very, very useful books that I found. So, texts for the multi-particle method, just recommendations. Okay. So the first case, I wanted to show some results for our semi-analytical model. So for this one, we decided to take a space-filling system. So we needed to choose what shape of the crystal we take. Now, we just mentioned this thing a little bit earlier. One of the things we do assume in these models is even if individually crystals are anisotropic, in an undeformed aggregate, the overall orientations of the crystals should be random enough that the overall fabric of crystals should be isotropic. So that's the idea here. And for an isotropic FCC fabric, we decided to pick rhombic dodecahedron as our choice of grain. So we have a unit cell of 14 grains here. And so what we do in these grains, we do a perturbation type approach. Okay? So our base state here is the cannonball stacking problem, essentially. So you have spheres that are packed in an FCC configuration, which have actually quite a high porosity, almost 33%. And then we perturb that spherical shape, this is the equation of the sphere, by a small perturbation. We also perturb a constant background surface tension with this perturbed surface tension. And when we plug in the solutions for velocity, solutions for pressure, hence the semi-analytical, because we solve for the solutions and velocities analytically using growing harmonics and decaying harmonics, then everything reduces to this, this equation in the shape of each of the grains. Okay? And then we can just resolve this, we can just solve this numerically using spherical harmonics. So pretty simple, but one of the nice things that comes out of it is basically we can vary the melt fraction, and that's what's happening here. We're just showing 3 grains, and you can see the tube is kind of shown here. The tube area is increasing as the melt fraction goes from about about 5 volume percent to about 25 volume percent. The color code is the degree of flatness. You can take that as an approximation for the area of grain-grain contact. So if I were to binarily digitize those would be the evolution of the contiguity. Okay. So we have seen some results of Takashi Yoshino's earlier on. So this is kind of a comparison of our results with von Bargen and Waff's model, which it fits quite well. The red diamonds are our data. Von Bargen and Waff, they reach, for these dihedral angle, they reach their cutoff at about 19 volume percent melt. Our segregation happens at around 0.25 or 0.24. We don't really match Takashi's data very well, and I have my own theories about that, which I think is when you are measuring from a microstructure, when you're measuring the contiguity on a 2D surface, you probably need to take into account any variations that could happen in the 3D, and that wasn't there. So, but there is some variations in that result. What's the most useful thing out of a simulation like that is I have the contiguity as a parametrized function of melt fraction. And it turns out if you are trying to do seismic inversion and other things, a parametrization like that can come in extremely handy. I'm going to show that in a second how. I'll skip that one actually.
Can I ask you this?
Sure, sure.
In a previous one, here you obtained the equilibrium microstructure.
Right.
So, but you have heterogeneous surface tension on your grain.
Mm-hmm.
You have deformation within grain.
Yep.
Yeah, that is very strange, I think.
Well, I mean, we're treating the grain as a viscous particle, right? It is a fluid flow problem. And if you impose a surface tension, you would drive some.
Even at grain, even at equilibrium microstructure, your grain inside is flowing.
Sure, but if you look at the picture, the movie that Uli was just showing of Nico Walter's model, you see during grain growth, you see deformation of grains.
At equilibrium state, we have no flow within grain.
So okay.
Because at triple junction, the difference between solid-solid surface tension and solid-liquid surface tension is balanced. So there should not be.
There should not be. That's true. There is no change. So I don't agree actually, and here is why not. I think we have a fundamental disagreement in terms of how we interpret the equations. In the equilibrium stage, this term becomes 0. That's the primary thing that's driving the shape. Okay. Well, you have to have some. You have to balance the stresses, right? If you have a surface tension that's varying along the boundary, there has to be some stresses.
No, there is no variation in surface tension.
There is a variation in surface tension between the grain boundary and.
It should be.
So the triple junction equation, the Young-Dupré equation that you're talking about, which basically, well, it's basically this equation that Uli was showing, right? Yes. So that's basically telling you what's happening at one of those points, and that equation is a simpler version of this case, really. So it's there, but there is more than just that. So I'm not saying that this is not happening. It is happening, but there is also more that happens. So basically, if you just think about this, if you just stress a solid body, if you somehow create some sort of surface tension, there has to be stresses inside. You cannot say that there won't be any stresses.
I hope you tell how you formulated triple junction in your model.
I don't. No, I don't, because I center everything on the grains here, right? So the triple junction is not an entity in my model. It comes out, but it's not something that I do. That's a big difference between the von Bargen and Waff model and my model, because in von Bargen and Waff, their origin is within the tube, and they model the tube as their body domain. I don't do that. I do the other way around.
It looks as if you're distributing the surface tension, variation in surface tension, over a region, rather than having it at a point. Rather than having it on the line.
It's true. It's true. I am.
It looks like, because otherwise you can't really take gradients of a surface tension.
It's true. So there, but it is a step function like variation, though, because it's not. It has to be on a surface, right? Because the grain-grain boundaries are a surface. It's just on the 2D section they look like a line. It is continuous, yeah.
Whereas yours is not.
But at equilibrium condition, it should be uniform at grain.
Equilibrium condition is df dt equal to 0. Okay. Okay. So in the boundary elements model, basically where we do this type of situation where we take these grains. So this is my 2008 paper, where we take the equations and we turn them into a boundary integral equation. So this is how our mass and momentum conservation equations taken together looks like. We don't need to spend a whole lot of time here, but all I wanted to show is that you have the velocity at the boundary of the kth particle, but you also have the unknown velocity inside one of these integrals. Okay, so this is called the Fredholm integral equation of second kind. So that's one of the challenges to solve this numerically. The other challenge is these two things here, J and K, these two kernels. These kernels are singular or hypersingular depending on which dimension you're solving for. So that means when 2 points on the boundary get too close to each other, these guys try to shoot to infinity. So every time you solve a boundary element problem, you always need to take into account of those. And then finally, once you have solved for the velocities, then you can update the shape of the grain, and you can update the position of the grain. Okay. So the discretization, I probably shouldn't go into great details, but typically for all boundary elements problem, and just not mine, hence there are no plugs. Generally, one of the methods that are very popular in multiparticle flow is using the method of collocation. So we use there is a Green's function, and that's evaluated at the boundary poles themselves. One of the things that's different between boundary elements and, say, for example, finite elements is typically the degree of interpolation is very high in boundary elements. So we typically use a cubic spline interpolation as opposed to just a P2P1 or Q2Q1 type element in finite elements. And the reason behind that is, well, twofold. First of all, as you saw, we need to know the information about the normals to the boundaries and tangents to the boundaries and the curvature. And the cubic spline actually naturally provides us those values. So for example, when we are looking into this triple, if we want to find what the Laplace force here, we know the curvature, radius of curvature at this point or at any of the points exactly. And then we interpolate the velocity field linearly.
Do you need to use monotonicity preserving splines?
Yes, within an element though, so that's fine. It works out. Except for what we call singular elements. So basically this is a geophysicist's attempt at depicting math. But if you think of those two terms that I mentioned before, the j and the k kernels within the integral, they have this type of behavior. So this is position x, and this is the value of the integrand. And what happens as you are approaching x equal to 0, it shoots to positive infinity on one side and negative infinity on one side. Okay. So the integral, these are called the CPV, Cauchy principal value integrals, because the integrals actually exist because these things cancel each other out. But when you're trying to integrate them numerically, they're a pain in the neck. So there are various techniques people use to do that. We use something called the radial integration method of Gauss, because that works pretty well for these boundary integral methods. And then the final part is updating the shape. So once we have solved for these velocities and we have obtained the velocity at each node on the boundary, then we use that equation that I was showing before to update the shape of each point. Steady state is reached when, well, there is no appreciable changes in shape. And we also are we have an adaptive mesh refinement, because when you have deformation, you could develop kinks and things like that. So we refine the mesh, and you can set whatever criteria you want. We typically use curvature at each element as a criteria. So if a grain gets above a certain value in curvature, if an element becomes too curved, we break it up into multiple elements. But then we can calculate the contact function for each grain, okay? And because we also know this number n at each point, we can actually evaluate contiguity. We can do that at each step of the simulation for each of the grains, which is really the massive power of this method. Because if you think about the experimental work, maybe sometimes down the road we'll be able to resolve the grain-grain contacts in synchrotron tomography, and we'll be able to actually measure the evolution of the contiguity in lifetime during deformation. But for now, at least experimentally, there is no real way to measure directly what happens to contiguity as you're doing an experiment. But these numerical simulations at least allow us to do that. So we have some idea of how you reach the steady state, what values are. So the one last thing, remember my mentioning that one of the downsides of boundary element model is that the matrix that results from the boundary elements is very dense. And the reason behind that is boundary elements typically involve point-to-point contact between all of the nodes. So this is this sort of communication that takes place. And that's what makes the equation matrix very dense. My PhD student, former student, Tyler Drombowski, finished his PhD at University of Maryland, where I was before. And he did this thing where he implemented a fast multiple expansion. And what that does, basically, fast multiple expansion, well, fast multiple was apparently the topmost algorithm in the 20th century. I have no idea. I just read it somewhere. But what it does is cuts down this crosstalk between the nodes and streamlines the communication. What you get out of that is basically when you have discretized your equations, you get a sparse matrix that has only dominantly diagonal entries, and off-diagonal entries are nearly or actually zero. And then, using that, we can go to much higher, much larger number of grains. So when we first did this work, the first pictures I was showing, I had 3 grains. And when Tyler finished his PhD, these are the 2 papers we published last year, and this was a pure shear simulation of 1200 grains, simple shear simulation of 900 grains, and we were able to calculate velocity, pressure, shape, contiguity of each of those. Okay, so here's the plug again. So I'm showing a couple of different cases here. So I'm going to focus more on the pure shear experiment. And these numerical simulations were actually quite a lot motivated with Martha Daines's work with David. Martha did these very nice experiments. We are still citing all of her work 25 years later. But she did these experiments where she would take a partially molten rock and she would compress, and then she would measure what's the orientation of the melt pockets. And what Martha found, basically, that the aspect ratios of the melt pockets change because of grain boundary wetting. Okay. One of the things I wanted to point out here, if you take a look at this contact function, and you can very clearly see that prior to deformation, the contact function is nearly isotropic, but it becomes very strongly isotropic. Sorry, not the contact function, the contiguity becomes very strongly anisotropic after deformation. So this was one of our primary outputs from this model. Yes.
Sorry for being ignorant, but what are the contours that?
So the contours are streamlines of flow. So basically, this is how the material is flowing within the grains and within the melt pocket in response to the applied deformation. Okay. So there are a couple of things. What I wanted to show here, maybe focus on this part. So we're looking at the ratio of the 2 principal values of contiguity. So the contiguity is a tensor now, and these are the 2 eigenvalues, psi1 and psi2, the 2 principal values. And what we see is as the aggregate shortens overall, this value becomes very far from 1. Okay? And 1 is basically when the contiguity is isotropic. So we get pretty strong anisotropy in contiguity as we keep deforming these grains. So what does that mean for our calculations? So here is the plot. Again, we're plotting 3 things here. We're plotting the trace of the contiguity tensor, which remains nearly constant or maybe shows a slight increase. And then we have these 2 components, the XX component, which is basically the contiguity arising from that surface, and the YY component. Now what happens in pure shear, you are pressing down, the grains are stretching horizontally, and more of the vertical boundaries are getting wetted. And this is very similar to what Martha noticed. And as a result, the XX version of XX component of contiguity is decreasing, whereas the other boundaries are getting drier and the YY component is increasing. Okay? So this is very similar to, again, the observations that were done before, except for in those cases, the measurements were done in the melt pockets, and Martha was measuring the aspect ratio. So
you're forcing the grain centers to remain, to follow the overall strain.
No, so what I'm...
Why don't they change neighbors? Because that would seem to me like...
Oh, they could. It's just they don't do that in pure shear.
They could. Perfectly well. They could remain spherical and just change neighbors, which is, the Raj-Ashby.
Oh, sure. But it's true, but we don't have that type of mechanism because in the Rajan-Ashby thing, actually one grain can switch into another. So
You don't allow that.
we don't allow that. Yeah, exactly. Sorry. Okay. So that's basically the initial cases. So I wanted to show a few applications of this type of work. So the first one is this has been used. We're using this for the third time now, and I have been working with several seismologist colleagues. And one of the things we have been able to do using this type of things is inverting seismic observations. So Yasuko pointed out one of the things that used to be the case with models of poroelasticity. People would assume that the melt occurs in pockets or tubules, okay? And that was not a very realistic description of the microstructure. So as a result, one of the things that had happened in seismology, especially of the deep earth for the large part of the 80s and definitely the 90s, where there was a reduction of shear wave, people would typically say, well, this is because of melting. And then quantification of melting becomes quite difficult because there is really not a very realistic case. Okay? One of the big examples is the ultra-low velocity zone at the core mantle boundary. There is this classic paper by Ed Garnero and Quent Williams when they first found it. They tried to calculate how much melt there is in the ultra-low velocity zone, and they used a model of tubules, and they found that if the melt does reside in tubules, then you will have 30 volume% melt in the ultra-low velocity zone. But as we saw from the microstructures now, when the melt goes to 30%, you basically turn into a mush. There are no tubules. So using this type of inclusion-based models could be really difficult in actually quantifying how much melt there is. So what we have been doing is something where, let's see, how do we do this? So basically we have an observed, I'm sorry about this, got a little bit pixelated. So we have an observed shear wave speed. We have a reference shear wave speed, what the mantle's shear wave speed should be, and you can use a mineral physics database. We use Lars and Carolina's data from Hephaestus. We could change this reference shear wave speed as a function of bulk composition and temperature in that region. And then we want to put all the anomaly due to the melt in this function. We call it the melting anomaly function, okay? And this melting anomaly function, we want to be able to vary that based on the dihedral angle, based on the composition of the melt, and of course based on the melt fraction. But the melt fraction is our unknown. We want to solve for it. Okay. So the way we go about that is we say, well, this Vs observed minus Vs reference times this melting anomaly should be less than some sort of cutoff value. And this melting anomaly function is this relatively benign looking thing where phi is the melt fraction, psi is the contiguity, except for the fact this exponent n here is a function of psi as well. Okay, so it's a messy little nonlinear equation, but you can write a little Newton-Raphson type solver and works out pretty well. So this is what we do. We actually take the observed value of the shear wave. We can take this reference value and then we calculate the melt. And one of the things that Benoit Tauzin and I have been doing lately, we were looking in the western US. And the reason for us looking in there was because we now have some data from the US area in this region. Okay? And in this specific case, we were looking at PS conversions. So, and we were what we get from the seismic signals is actually an amplitude of reverberation. And we convert the amplitude to a shear wave speed, and then we run our analysis on that. So I'm just going to get to that. So these show our stations from which we could actually get reasonable data, and I think there's about 680 of those. And along this white line, we are looking at this transect, okay? just to guide your eyes, we got the 410-kilometer discontinuity, and then we have this blue region, which we call the low velocity layer, okay? And that region shows about 2.5% drop in that amplitude of the shear amplitude of PS conversion. So we ran this analysis, and I actually showed an earlier version of this map in my previous talk, but this is the first map of melt percent in the western US for the 350-kilometer depth. And we ran this for various potential temperatures, various compositions, but basically what we come up with in this region, we get an average approximately 1 volume percent melt. It might be quite interesting, actually. I was just thinking about when you guys were talking about this sort of permeability threshold cutoff situation. I mean, this is kind of straddling in that region, and well, if our calculations are right, we're seeing melt go pretty far from the subduction area. So maybe we can kind of do some sort of constraining from these calculations in what we see in nature into what you see in the lab. So anyway, so this is one of the useful calculations of this. What we could also do, we could actually also calculate electrical conductivity too. And this is a map of the bulk conductivity. So Leila and I worked with Fabrice Gaillard. We got this paper by Cifre et al. And what Fabrice's group was doing, essentially, they were looking into how CO2 and H2O changes the conductivity of basaltic systems. So we could do this type of forward modeling of bulk conductivity based on the melt volume fraction that we get. Also, there are a couple other cases. Anna Courtier and I did some of the work using that same code, MuMap, to calculate melt volume fraction, where we had this contiguity melt fraction characterization, and then we were able to calculate that melt volume fraction near Australia and Hawaii as well. Okay. Second case, forward modeling of seismic anisotropy. All of us looked into the melt preferred orientation or grain boundary weighting and banding quite a bit, so I'm going to kind of skip that. There is this interesting work that Yasuko's lab did, where she basically studied the reversing the state of stress on a grain, and then shooting seismic waves through that. And I think, if I'm not wrong, I think this is probably one of the very few studies that actually measure the change in seismic wave anisotropy during deformation. So this was quite unique, actually, in that way, and quite helpful. So what we did, we took the anisotropy development, the pure shear case that I had shown you earlier, and we wanted to see if there is a connection that we could explain. And one of the cases that has become quite interesting for us is the lithosphere-asthenosphere boundary. When year before last, there was a paper from Caroline Begin's group in Science, where they showed there was a very interesting pattern that happens, especially near the old oceanic plates. Near the young oceanic plates, you get this region that's marked by beginning of seismic anisotropy and reduction of shear wave velocity. That's the Gutenberg discontinuity and the beginning of the low velocity zone. But then those two separate out as you go into older oceanic crusts. So you have the anisotropy, seismic anisotropy, set in earlier at a lower depth, and the low velocity zone still follows an isotherm. So Tyler and I looked into this case and wanted to see if we could do something. So just a little extrapolation from our experiments, and this is a similar type of cartoon that Ben Holtzman has shown before, but we could calculate this shear wave splitting for different orientations of these grain boundaries, and what we get is basically, now what you probably don't see here is each of these data points here is actually 1200 data points. So basically we're calculating this contiguity and the delta Vs in the x and y direction, the shear wave anisotropy for each of the grains in the aggregate as they deform. And then this is the total seismic anisotropy that we're seeing. And you can see by the time we get to about 48% strain, we're kind of approaching a steady state value for this, which is around 3 volume percent. Okay. So basically, what we think is if we take our value of what we get from our results, that's this vertical line here, and then if we compare the curve, this is from Caroline Beguin's model, this is actually VSH over VSV squared. We are assuming that the grain boundaries are weighted in a horizontal direction. We do a pretty good job of matching the observed seismic anisotropy by this type of grain boundary weighting. And we are not really very unique in saying this. There was a Kawakatsu's Millefeuille model which suggested that, and several other people before us suggested that. But the nice thing about this is this was actually a rock deformation simulation from where we could actually calculate this type of behavior. Okay. And I'm running out of time, so I'll just very quickly go through the very last part here. For melt migration models, I'll just show a movie because it's cool. This is a dive here. That's all. Okay, so the other part that we have been kind of interested in is melting above the transition zone, also trying to look into the model of melt migration, and not so much detail about what's going on, but this is melt is being generated, and there is a new work by Mike Walter's group where they were showing that actually if you have carbon dioxide in your basaltic crust, you could actually, the CO2 survives all of the dehydration that happens around 100, 150 kilometers, but there is a very strong ledge in the curve for the CO2 solidus. So you can actually generate a melt that kind of spreads like a gravity wave. What I wanted to show really is for those of you who are doing geodynamical simulation, I have MuMap on, I should have codes, I'm very happy to share it with you. Those of you doing two-phase flow simulation, and if you want to do this type of calculations, so you can calculate the contiguity, Vs over V0, conductivity, shear modulus, bulk modulus. It's very easy to do all of that. So if you're interested in doing this type of calculations based on nice microstructural models, you could do that as well. Okay, I'm going to stop there. My summary is I talked a little bit about techniques for modeling microstructure, talked about the semi-analytical and fast multiple models. Use the contiguity to do this forward modeling of elastic properties, seismic signal inversion, and the forward modeling of electrical and elastic properties. We'll probably look forward to doing some rheology calculations sometime soon. And I would be really interested to get some models on the 3D finite fast multiple boundary element model. And we also need some better averaging models for when we have an anisotropic structure. Okay, I'm going to stop with that.
All right, time for questions. Yeah, Neil first.
Yeah, boundary element methods tend to run into trouble, I think, when the droplets or grains are very close together. Is there a way you get around that?
Yeah. So what we could do is basically we deliver this thing called the nearest neighbor algorithm, because so our grains can see each other, and our grains can know which of the grains are closest to that. So basically we create this information pattern where we store the information for each of the grains and their neighbors and the neighboring nodes. The other part that I think you're talking about is also the film drainage problem. Is that right? So when you get two blebs very close to each other, we still have that issue. So in reality, we have, it's almost like we have a very thin layer of film that stays in between the grain boundaries. But if you look into any of the microstructures that we have, even the 2D microstructures, so that film is pretty thin. So we are still able to keep them pretty close to each other. So generally, that has not been so much of a problem because of the nearest neighbor approximation.
Even though the X-ray tomography cannot solve the solid boundary, but right now we focus on the fluid part of the transport property. but we do say plot all the zeros, which is the solid part.
Mhm.
Right? Yes, we don't see where the contiguity are because you can't tell it's a solid.
But you do have the CPX and olivine grains, though.
Right, that we have. But I'm asking you, then would you be, because right now my understanding is that you generate those microstructures, but would you be able to take that solid phase?
That's what I would really love to do. Yeah, I would really love to be able to do that. So I could read that in a grid, and then I can run the simulation to
That
that.
would be great because
Yeah.
these are the solid.
Yeah,
phase,
absolutely.
right? So you could run that.
Yeah, absolutely.
Simulations.
Yep. And Lars and I had been kind of talking about doing something similar also. But yeah, I mean, I think that will be really great actually. So just
Awesome.
these 3D tomographic images
Right,
coming
because
in as an input.
yes, you cannot say, oh, well, here is the olivine touch olivine, but as a whole aggregate, you can calculate it.
Yeah, absolutely. So we can share, we can do a virtual sharing of your aggregates.
Wouldn't
Yeah.
that be great? So you can do that, right?
Yep, absolutely.
Yes.
Since I live in Utah, I noticed your map of the western United States, you know, the melt fractions. And I sort of saw, it looked like where the Great Salt Lake is, there was either no data there or whatever. I was curious, you know, I didn't quite pick it up, how you generate your waves, and what's the kind of the takeaway from, you know, what are you inferring about?
About that?
Yeah, about what's going on, under, you know, and there's all kinds, like a super volcano or something up in Yosemite.
Well,
and
there's
all, you know,
Yellowstone very close
yeah,
by.
Yellowstone, yeah, yeah.
So, okay, I'm sorry, let me just take 1 second here. Let me show this one first, okay? So let's first take a look at this picture. So this is from this is Tajan et al. 2013, I think. So this is along that line here, okay? So what happens here, we got this little thing called the Gorda microplate that goes into the transition zone, and then it kind of stalls in the transition zone there, okay? And then what we see, let's go back to the map of the melting next. What we see here is, well, we don't have a whole lot of data coverage here. We have data, there is some seismic data here, so we have data for the thickness of the transition zone and stuff like that, but we don't actually have data here that was good enough to transfer, you know, like get the melt fraction value out of those. Yellowstone falls somewhere just outside this boundary, okay? But remember also though, this is at 350 kilometers below the surface, so, you know, things could bend around. There is, what this thing correlates with extremely well, there was an article I saw, it was Derek Schutt who did, and it was actually an AGU poster. He had a map of the temperature of the base of the lithosphere, and he sees this very strong bifurcation in the temperature, just like we see. So we see this sort of this region that has a relatively high melt, and it tapers into a low melt fraction, kind of, if you think of this, it's almost like yeah, so it kind of tapers off like a gravity wave that's riding on top of that Gorda plate and heading towards the east. So that's our story. I mean,
Things you can really infer.
yeah, so the way we infer this is basically we think it could be possibly related to carbon dioxide related subduction, and if carbon dioxide related melting, and if that is the case, then we do think that that can be a huge carbon sink in the mantle. You could actually store up to 60% of the mantle's carbon in that sink there. So yeah.
A very simple question. Which is the melt distribution you are using when you are doing these inversions? An anisotropic one or something else?
The isotropic one.
So
Yeah.
it could be very different because
It could be very different.
The sampling is directional, it's not isotropic.
Yeah, so we don't have any, so one thing is, we don't have any data on, at least the data set we are working on with, we don't have the shear wave splitting data for this region, but also we don't know quite yet how to do the full inversion. I haven't done that quite yet, but I'd love to do that.
The boundary element methods, you were showing results where you have this grain and you start deforming it on a pure shear. But if you have enough grains, and you just let the whole thing sink under gravity, you should theoretically get porosity waves or solitary waves. Something you have tried?
Sure, but there is no gravity in these ones, right? Because this is simulating the. Oh, people. Yeah, people have done that. People have done that quite a lot. So, so I don't think people have looked into porosity waves in that, but people have done these for rigid crystals. There are two classes of work. Some people have looked into crystals settling in metal alloys, and then the hemodynamics modelers who model platelets in blood, they use that same type of thing too. They let those things sink with the gravity or have a flow move. I haven't done that with gravity, but yeah, you could do that. And you should be able to see solitary, or I don't know actually if you could, but you could see wave-like behavior.
But aren't those models of like platelets and blood and the disaggregation limit? So it would be a different physical limit than.
Sure enough, in these cases, the disaggregation limit is about what we see in the lab experiments as well.
One last question. All right. Well, let's thank Sash again.